Well, hello, everyone. Thanks for joining us in person or virtually. My name is Yafeng Yin. I'm a professor and interim chair for the Department of Civil and Environmental Engineering at the University of Michigan. So welcome to University of Michigan Building the Future Distinguished Lecture Series. So in 2019, our department completed a 2-year strategic visioning process, and through which we identify 5 strategic directions, which are enhancing human habitat experience, shaping resource flow, automation, adaptation, and smart infrastructure finance. So our strategic vision reaffirms our value proposition to our communities and reinforce our commitment as engineers working in service to society. And to highlight our vision and to formulate a work plan, and we launched this Building the Future Distinguished Lecture Series. So it's aimed to build a broad community that includes industry professionals, researchers, educators, and students, and through presentation from leading experts and also panel discussion. So this series provides new insights and explore a range of perspectives that on those 5 strategic directions. So the direction covered by today is adaptations. So this direction advanced new approaches to adapting the design and operations of infrastructure systems and to ensure sustainability and resilience in the face of dramatic global changes. So we have had a lot of support for this to make this vision and today's webinar come together. I'd like to thank the co-sponsor for today's events. So they are American Institute of Steel Constructions, Engineering Mechanics Institute of American Society of Civil Engineers, Exponent, Newport, Simpson, Gumper, and Heger, Skidmore, Owings, and Monroe, with Janet Elsner Associate Incorporated. I would like to thank the Strategic Implementation Committee led by Professor Sanyong Lee. I also would like to thank Evgeny Filipov, who is assistant professor here at the University of Michigan. Professor Filipov has agreed to be the moderator for today's presentation and panel discussions. I also would like to thank Joyce Kennedy and Michelle Santayam and Mark Khalil Snyder for providing technical and marketing support to today's webinar. Now I'd like to turn this session to
So I would like to welcome everybody for participating in today's event. Today's distinguished lecture emphasizes the strategic theme of adaptation. To give an overview of this theme, I would like to play a 2-minute video.
Adaptation is a necessary thing for survival. We're dealing with many things that are affecting our life. Climate change is essentially raising sea levels, and that's going to affect coastal communities. It will cause more severe storms, more severe hurricanes, and tornadoes that are becoming increasingly frequent and increasingly destructive. We are looking at how extreme events like hurricanes and earthquakes affect communities, and how can these communities recover quickly from these different types of events. My colleague Evgeny Filipov, he is looking at how origami can help us design structures that change shape, that respond to various types of hazards as they occur. My colleague Valery Ivanov, he's looking in the Amazon at how trees interact together and how they grow within that environment. My work is focused a lot on earthquake engineering. If we do not build our structures to be resistant to earthquakes, we are going to get structures that would fail in a catastrophic manner. We will always be adapting to new stressors that will appear on the horizon. We just don't know what they are yet. Through human ingenuity, we will always be able to adapt to whatever situation exists.
So during our seminar, online participants are invited to submit questions through the Q&A function on Zoom. And at the end of the seminar, we'll have a panel discussion. And during that session, we'll try to get through as many of the questions posted online, as well as some of the questions from our in-person participants here. Now, I'd like to introduce to you our very special speaker and panelists. We're very fortunate to have Jerry Hajjar, Professor and Chair of Civil and Environmental Engineering at Northeastern University. He will speak to us today about the topic of urban engineering, new strategies for resilience and sustainable future. The presentation by Jerry will be followed by a panel discussion with our distinguished panelists, Larry Kruth, Jason McCormick, and Tabitha Stein. Larry Kruth is owner of Kruth Engineering and former vice president of engineering and research at the American Institute of Steel Construction. Jason McCormick is a professor of civil and environmental engineering at the University of Michigan, and Tabitha Stein is general manager of construction solution services at Nucor Corporation. This brings us to today's distinguished lecture. Let me now invite Jerry to speak on this theme and give his presentation.
Okay, thank you very much, everybody. Evgeny, thank you for the invitation. Great to be meeting with the faculty today, my first time here at the University of Michigan. So as Evgeny said, I'm going to speak today about a number of new approaches I've taken over the years to look at resilience and sustainability in structural engineering for the built environment. Today, I'm going to especially talk about our work in buildings. And I think the video framed this quite nicely in that, in that we are increasingly looking globally at impact of what's happening in different countries on our profession, new design strategies that they're developing, influence of supply chain, impact on climate change. We're increasingly thinking holistically about complex urban regions. For example, I've been meeting with the embassies in United Kingdom and France, both of whom have set major goals for having net zero embodied carbon by 2050 and are well aware of the influence and importance of civil engineering and structural engineering on achieving these goals. It's a time when we're looking at the types of decisions that we've made over the years in civil engineering and structural engineering, starting to think about social equity, social justice, and whole new ways of framing our decisions and impact on our designs. We have 60% of the world living in fragile coastal communities that are certainly increasingly affected by climate change. And as structural engineers, we're thinking increasingly and directly about the environment and its influence on our designs. Some of this has been captured by American Society of Civil Engineers in their recent Future World Vision, led by Jerry Buckwalter. And he said, change is coming, and it's on a scale that can really drive confusion and dysfunction unless our profession is ready to address these new realities head on. But it's an exciting time. You could see some of the topics that the Future World Vision addresses related to smart cities, high-tech construction, advanced materials. So much of this starting to influence how we think. I've been able to go to Kobe, Japan over the years several times. It's a beautiful city in central Japan, along with Kyoto and Osaka, forms a triumvirate of cities that are an economic hub. Kobe, one of the most important cities in the history of Japan. When I go, I stay at the Portopia Hotel and can overlook the port facility and see the activity. However, the city was highly impacted January 1995 by the Kobe earthquake. And this was an earthquake that was on the high side of a moderate earthquake, certainly not the big one. But fire raged throughout the city from gas explosions. Kobe, perhaps the most seismically, Japan rather, the most seismically prepared country in the world. Yet they had some significant collapses in their building. Transportation infrastructure impacted heavily. But most importantly, the port facility was basically wiped out by the earthquake. And of course, we see this over and over again. 2008 in China, 70,000 dead. 2005 in Pakistan, whole villages leveled to the ground. Oops. 1976 in China, hundreds of thousands dead, often from lightly reinforced concrete and masonry. But these are not just issues of the past. Just a few weeks ago, of course, the East Anatolian Fault in Turkey had several ruptures to it. And we're seeing here not only the impact of vulnerabilities from lightly reinforced concrete and masonry, but also the impact of corruption that can occur in our profession. And we'd like to think it doesn't occur much in the United States. But if we look at what's happening around the world, we still have a long way to go. You know, Japan's so well prepared, and yet you look at 2011 with the impact of the tsunami on the Fukushima nuclear power plant, and that whole region is still struggling to recover. In the structural engineering world, we have a term called disproportionate collapse. And here we speak about damage or collapse that occurs to our structures disproportionately to the amount of load. Perhaps first discussed with the Ronan Point collapse due to a gas explosion that we see here. But the term really wasn't thought about too much for several decades until 9/11. And I think most engineers would agree that the collapses here were not disproportionate to the loads. But increasingly, we started thinking much more directly about collapse simulation, modeling collapse, and thinking about the impact of collapse on whole regions. And you can also talk about disproportionate collapse of a region. And Hurricane Katrina 2005 provides a clear example where the failures that occurred in the levees wiped out whole populations, neighborhoods in New Orleans that really still have not covered adequately. Kobe was the 6th largest port in the world at the time of the 1995 earthquake. And I visited over the years following that, and it still struggled to recover. A lot of the shipping lines at that port, it was largely a through port. They redirected to other ports, formed new relationships. Much of that economy never came back. And this at a time when shipping traffic was rising exponentially. But this is not just impacting the rest of the world. Certainly high seismic zones, high hurricane zones in this country still have vulnerabilities. High seismic zones out in the West Coast. I know just last week, the president of the Earthquake Engineering Research Institute, with support from a number of other professional organizations, went to the governor of California and pointed out quite clearly that the types of failures that we saw a few weeks ago in Turkey absolutely can happen in California still. And they've been making great progress, retrofitting schools, hospitals, bridges, other critical facilities. Some of the cities or counties have laws on the books to try to upgrade privately owned structures like apartment buildings and such, but it's taking decades and we have a long way to go and these vulnerabilities are there. So Kobe was a through port. What do we do with a port like Los Angeles and Long Beach? This is a destination port for a huge amount of the goods that come into the United States. And if we have a major earthquake in Southern California, the impact on this country can be lasting for a long time. We see something like Superstorm Sandy, which hit New York and Boston quite hard. The recovery was fairly quick. But I think we do need to step back and ask ourselves, what does it mean to be resilient? How do we develop systems that can bounce back quickly from extreme events? Simultaneously, I think we have an imperative to really be leaders driving on sustainability in the built environment. Construction and use of buildings takes about 40% of all energy use, about 40% of all material resource consumption, about 40% of all waste production, about 40% of all greenhouse gases. Transportation sector, another 30% of energy use. Industry sector, the remaining 30%. So civil engineering certainly has a huge role to play, and I'd like to see us right out front on this topic. We have a long way to go. I think the way in which we're designing now, I call unsustainable engineering. This is a diagram from my friend David Barr. For those who are not structural engineers, the way in which we absorb the energy from an earthquake or a hurricane, for example, is by having material damage, largely by having material damage in our primary structural components. We have yielding, of steel, crushing of concrete in the steel columns, in the girders, in the braces. We design ideally not to collapse, except perhaps in the most extreme loads, but we don't design not to be damaged. You could have a brand new structure designed to code, and if you have an extreme event, it might be so damaged that it has to be condemned. We put this under the category of assessing risk and having reasonable risk, but I think we can do better. And I'd like to talk about a few solutions I've been looking at over the years to try to address some of these topics. One that goes back a number of years with Greg Deerline, Helmut Krauwinkler, Sarah Billington at Stanford, we call a controlled rocking system, and it provides an example of a number of different kinds of systems that have now been developed over the years. This one takes two steel frames, and there's three components to the system. First, we put it in a trough to allow it to rock free from the foundation. And then we use that motion to engage replaceable energy dissipating fuses, I call them, like the old fuses in your basement. These are the gold plates. These are standard steel plates with diamond shaped cutouts. We call them butterfly fuses. And once you put those diamond shapes in there, they can deform 30 or 40% of their original dimension without fracturing prematurely. And then the third component is in green, the vertical post tensioning. That snaps the system back to vertical. Then you can pop out the old fuse, pop in the new fuse, ready to go again. And so we tested this in a number of different ways, quasi-static tests and such, but we culminated with some shake table tests at E-Defense, the largest shake table in the world outside of Kobe. This is one reason I was going there. A little different configuration here with a single frame with a white post here. And as the frame rocks back and forth, the white post goes up and down and engages the fuse at the bottom center. You can see a photograph here with the specimen being put into place, the specimen in gold. And this is being slid through in gray, some large masses on linear sliders that will shake when the shake table shakes and throw the inertial force into the specimen. On the right, you can see a person to get an idea for scale. And this video will show a large earthquake that we subjected this system to. On the lower right, you'll see the linear sliders, the masses sliding relative to one another. On the upper half, two bases rocking back and forth. And then on the lower left, fuse in action here with the post tensioning. The system is very robust. Oftentimes, you might not even need to replace fuse. And of course, the idea here is that the rest of the frame stays damage free. And so if you look at typical results, this shows basically load versus deformation. Full hysteretic loops, as we call them, show the energy dissipation from the system, but then it all comes back to zero as it self-centers. And, these types of systems deflect about the same amount as current seismic force resisting systems that we use. And through the self-centering, if you detail the rest of the connections in the structure, you could self-center this whole system. So we've been working for some years to determine how to get this best into the building codes. It's really a whole new approach because we have stiff elastic spines versus failing on a story-by-story basis. So it's going to take some work. There have been some early adopters. For example, the Orinda City, California offices, David Marr, had his replaceable fuses be deformable angles down at the base, like you see here. And then you could see the post tensioning going up the inside of the column. And then you could detail the connections to be able to handle the rocking motion through slotted connections or perhaps pin connections like we have at the top here. Luth used the butterfly fuses in the USC School of Cinematic Arts, here using precast concrete planks instead of the steel brace frames, again, keeping those damage free. Configuration very much like E-Defense, but here with a buckling restrained brace for the post. And as I said, there's been a variety of different solutions over the years. This is for the Hewlett-Packard Foundation headquarters. Tesla Gigafactory in Reno, Nevada, using this system. And so we've been starting to map this onto different kinds of structural systems. For example, Jim Lefebvre and Larry Fonstock and I at University of Illinois looked at standard elastomeric bridge bearings that are there to have temperature control. We put these through high seismic motions for a mid-America earthquake, and we could start to see that you can isolate the superstructure of the bridge, isolate the substructure, and have these systems greatly reduce the amount of damage. Similarly, in recent years, been looking at hurricanes and doing some fully nonlinear analyses on transmission line towers for a complete hurricane, many hours worth of loading. And then looking at the difference as seen on the lower left in the fragility curve, having different types of solutions here to try to make this system more resilient. So we avoid the types of collapses we're going to be seeing in extreme events, like in the photograph. Simultaneously mapping onto these systems approaches that can be more sustainable. I'm pleased to see all the activity increasingly going on in our profession. I'm a big supporter of SE 2050, which is a movement to get structural engineering firms to commit towards educating their engineers on these topics, reporting on sustainability metrics of their structures, and moving towards net zero embodied carbon. If we look at our typical construction materials, concrete is largely downcycled right now, about 20% of it recycled. Timber, very hot among the student body nationally, structural engineering students going crazy over timber. About 60% of it right now going to the landfill. I hope we can come up with new solutions that could do better than that. But steel is a fantastic material. Comes just about from 100% recycled material now, and about 100% of it goes back to being recycled. And increasingly, as we might hear from our panelists, using renewable energy for the creation of the steel. Lots of opportunity there. So one project we've been working on in recent years is Design for Deconstruction, funded by AISC and the National Science Foundation. Working on this with Mark Webster at Simpson, Gumpertz and Hager. And here we're looking at replacing a cast-in-place concrete floor with precast concrete planks that you can clamp to the top flange of a building floor system of a steel beam to achieve composite action. And we envision this being in a floor plate with this jigsaw pattern of these precast planks. They can come in different widths, different lengths, and we envision them being stockpiled both as new planks and steel beams, and then disassembled and stockpiled for reuse after the life of the building has been achieved. Oftentimes buildings are taken down because owners don't want them anymore. They haven't been subjected to extreme events. There's a lot of opportunity here. We see this in use with all bolted steel construction, so you can take the whole system apart. This is already starting to happen in Europe. And we ran a series of tests to document the strength on these systems, push out tests like on the lower left, where we're pushing the steel beam past the concrete plank so that we understand the shear strength on the clamps. And then on the right, full scale beam subjected to gravity load so we can see the composite action. And for the push out tests, we ran a whole series of tests, monotonic loading, cyclic loading to get ready for high seismic applications, and different numbers of clamps here. And suffice to say, the clamps work beautifully and they can hold their strength, or certainly near peak strength, for very large deformations. It's essentially a damage-free form of force transfer. And of course, engineers are pretty nervous using friction as a force transfer mechanism. I understand that. But I think in a controlled configuration, such as a gravity beam, there's a lot of opportunity here. And then similarly, we did 4 full-scale beams. These are about 30 feet long, different member sizes, different percent composite action. So different numbers of clamps on here. And showing here load versus center beam deflection. Loading and then unloading the system to show that it retains its stiffness quite well. And it holds its peak load for very large deformations with no degradation. So we think the system has a lot of promise. If you calculate estimated design strengths, for example, using current design strategies from AISC for composite beams, these are achieving composite action as we would expect. In recent years, we've been working on Steel Diaphragm Innovation Initiative. This is Ben Schaefer at Johns Hopkins leading this project, Matt Etherton at Virginia Tech, Sam Easterling at Iowa State. This is funded by NSF, AISC, and a number of other steel organizations. And in this project, we're looking at current construction, but it's going to be leading to some newer projects that I'll tell you about in a moment. We're looking especially here at the three-dimensional behavior of steel building structures and the flow of forces that occurs during an earthquake in the floor diaphragms, composite steel deck floor diaphragms. We have surprisingly few design provisions on how to design the diaphragm. We leave this largely to the engineer's judgment right now. So this project was to try to advance that. We did a whole series of experiments and analyses and then recommendations for design. I'll just show you one brief window into this. The project culminated in a full-scale diaphragm test that we did at Northeastern. This diaphragm is about 30 feet long, about 24 feet wide, about 10 feet tall. And we had a series of 4 in-plane actuators here that are going to be cycling this back and forth at the distribution of forces that a diaphragm would see in a large earthquake. And this is a rare kind of specimen because it had indeterminate steel framing. It had a number of steel framing for the gravity system. The key beams are the one on the left and right, the south and the north, that we call collectors. These are going to transfer most of the shear from the earthquake out of the diaphragm and down into the lateral system. We had a lot of instruments on here, had standard construction practices like we'd see in the field. So a little bit of reinforcement around the perimeter, but otherwise not too much reinforcement in the concrete. And this time lapse will show you the results from the cyclic loading that was applied here. And most of the damage occurred on the outer 2 bays. We had 3 concrete pours because the slab was so large. We ordered the exact same mix design and we got 3 pretty different mixes. So I think those of you out there who are in the concrete world, we still have some issues to address. And so the damage is going to be occurring mostly on the right side here. The concrete was a bit weaker. However, the strength and stiffness of the diaphragm was huge. And overall, this performed really well. I think we can have certainly faith in our current floor systems and also now a better understanding of how they work. But with respect to the topic of resilience, if you have significant events and get cracking like this or crushing like we see on the right, I have to ask, is this really the best we can do? Get a sense for the load hysteresis, load deformation hysteresis here, well above predicted design strengths, holding the load for quite extensive deflections. So this has led to last couple projects I want to talk about. These are just starting off. First one is called Fast Floor, looking at the behavior of modular steel plate floor assemblies. This was done with the same team as SDII, along with Oner Avshi at West Virginia University. It's part of the AISC Need for Speed initiative, funded by the Pankow Foundation, AISC, and other Nucor and other organizations. And we're looking here at developing an all-steel structural system. So in particular, a steel floor plate system, no concrete in the floor for standard steel buildings. And not only are we looking at removing the concrete, but having a modular system that could be much faster to construct. And I would add, potentially could make this deconstructible. Looking at recycled steel, of course, increasingly from renewable energy, we can achieve a lot of different objectives with a system like this. And so we're looking at having 2 beams, a 10-foot wide plate that is asymmetric. And so the edge of the plate would drop down on the neighboring beam. In this system, a typical module might be 40 feet long. And this video from Clark Construction compares the potential for fast floor construction with typical construction that we have on the right. And so on the right side, putting in the steel framing, laying down the metal deck, pouring the concrete. On the left side, popping in the fast floor modules. And the savings that this construction company and others that we've interacted with are predicting can be quite substantial. This means cost savings, potentially material savings, and perhaps most importantly, eliminating the concrete. So the fast floor system's finished here, and on the right, they haven't quite gotten up pouring the concrete yet. I think you get the idea. The other project from Department of Energy is looking at cross-laminated timber floor diaphragms in steel building structures. And here we have a large team at Northeastern, along with folks at UMass Amherst, Swarthmore, Simpson Gumpertson Hager, and Opal. And both of these projects are for seismic engineering. And so in this one, we're going to be pulling together a lot of the ideas that I have talked about. Design for deconstruction, using the cross-laminated timber diaphragms. I'd like to see if we could isolate these relatively brittle diaphragms from the lateral force resisting system with some butterfly fuses. We're going to be looking at advanced materials in the layers, the the CLT diaphragms to address acoustics, vibrations, fire. So that'll be work moving forward. Now, a lot of you are probably familiar with LEED. Many buildings now design with LEED to try to achieve better sustainability. I'm not quite sure LEED is doing everything that we would like, but at least everybody is talking about it, designing with it, understanding it. The U.S. Resiliency Council out of the West Coast is trying to do the same thing with resiliency, where they've established a silver, gold, and platinum rating system so that in addition to rating your structures for sustainability, now you can rate them for resilience. And sustainability is certainly critically important moving forward. But as an owner and an occupant, resiliency is the real deal. Understanding whether your structure is going to come back quickly after an extreme event, I think is increasingly important, so that unlike the Goldman Sachs headquarters, which was an island of resilience planning amid a sea of darkness after Superstorm Sandy in Manhattan, we could start to do better. A few years ago, I had one of my postdocs and I did a little bit of work in topology optimization, which is an approach where you represent, for example, a building with a mass and apply loads to it, and then it tells you how to redistribute the material to address those loads in an optimal manner. And a number of structural engineers out there are using this increasingly in some of their designs, and these provide shapes that are very organic, and they really just feel right. They're very efficient. And in fact, some of these shapes have been around for a long time. And I'd like to increasingly pull a lot of these ideas together, for example, to think about topology optimization of regions. And increasingly, as we design individual structures, thinking about the communities in which they're being put and the impact of their performance on those communities. You know, with respect to sustainability, I think this is going to require a culture shift. Whereas engineers, owners, general public, if we design something and put something out there that's not sustainable, it feels ugly. And if it's not resilient, it feels dangerous. And so I hope you all will join me in trying to shift the profession more strongly in these directions. Thank you very much.
Thank you, Jerry. And now we're ready to move over to our panel session. And the way we'll do this is we'll have our panelists introduce themselves, and we'll then move over to some questions from the audience. So you all know Jerry, but then we'll start over. This is Larry Cruz from Cruz Engineering. Larry, maybe if you can give us a quick introduction and maybe your thoughts on the seminar and overall this theme of adaptivity that we've been talking about today.
Okay, my name is Larry Cruz. As you said, I'm owner of Cruz Engineering. But prior to that, for the past 6 years, I was Vice President of Engineering and Research at AISC in Chicago. Well, prior to that, I spent 31 years as a fabricator and erector for Douglas Steel in Lansing, Michigan. So I have a background in construction and in engineering and research. But as Jerry was talking about, he talked about a number of things that AISC had participated in, but he talked about fast floor. And one of the unique things about fast floor is AISC did a research project on evaluating timber buildings versus steel frame buildings. And it's found the global warming potential for both is about the same. You know what contributed the most to a steel frame building to global warming potential is the concrete on the floor slabs. 50% of the global warming potential from a steel frame building comes from concrete on the floor slabs. Using fast floor eliminates that concrete, will help the sustainability of global warming in the environment.
Thanks, Larry. Next, we have Jason McCormick, faculty here at the University of Michigan.
Thanks, Evgeny. So as Evgeny mentioned, my name is Jason McCormick. I've been a faculty member here in the Department of Civil and Environmental Engineering for the last 15 years. I also sit on a number of committees with AISC, AWS, ASC. So been involved on things associated with steel design and a lot of research involved with steel design. In terms of kind of adaptability and what Jerry mentioned in terms of his presentation, I think it's really important that we consider how we're using materials going forward, right? It's not just about creating a building for what is specifically needed now and the loads that you expect right now, but understanding how that building's gonna change and need to adapt over time, and what using a material actually means, what the embodied carbon is associated with that particular material and how that may change over time as well. So I think adaptability falls into this understanding, and I think we need to do a lot from a research side and also the design paradigm going forward, changing that so that we're thinking more globally and long-term in terms of what we're doing.
Thank you. And last, we have Tabitha Stein from Nucor Corporation.
Sure. Hello, I'm Tabitha Stein with Nucor Corporation. I'm a general manager of construction solutions and structural engineer by trade, and I've been at Nucor about 3 years, and prior to that spent 16 years at AISC with Larry and on committee work and efforts with the industry, and prior to that was a design engineer using steel and other materials. And as we think about this and wearing the hat of a structural engineer at a steel industry and realizing the carbon that is used in buildings, as Jerry talked about, but also just the carbon that is in the steel industry in general, and the responsible sourcing of materials, adapting structures for the multiple uses that we can't anticipate today. The structural engineering world is morphing in the over 20 years of my career of the responsibility to the future, not just the economical design of what we need to do today, but anticipating what's there in the future. Structural engineers are having more of a seat at the table with the policymakers, with the owners and practitioners that are setting these standards, and how we can ensure that the best structures are the one that responsibly uses the right materials all together to achieve those goals. And it's a moving target, and it's going to continue to move, and the opportunity we have to write those goals and standards, I think, is immense.
Thanks, Tabitha. So again, I'll state for our online participants, if anybody wants to ask a question, we have the Q&A option open. Please feel free to submit questions. I have one here from Raymond D'Adazio at Torton Tomasetti to kick things off. So since most structures that will exist in, say, 2070 exist today, how will retrofitting existing structures be addressed? And maybe I'll start with Larry, if you want to give some thoughts on this question.
Yeah, it's a very interesting question, because I think the future is adaptive reuse. And I think reusing old structures for new purposes is the best solution. I'm going to give you an example. Locally here in Michigan, Lansing, there was a power plant that was built in the 1930s and sat abandoned for 25 years. If you go to that power plant today, it was adapted into a Class A office building without disturbing the original structure, reusing the structure, relocating some steel inside for beams and things like that had to be added, reuse the entire exterior and interior of the structure. And it's a very attractive, very pleasant structure to be in. So reusing old structures that sit abandoned for a long period of time is the future. Do not tear things down and build new. Adapt, reuse.
Yeah, I'll just add on to that. I've had a unique opportunity. About 6 months ago, I sat on a jury for project awards. So imagine people submit projects that they've built and designed all over the world. And a lot of them are high rises, and high rises that are the eye-catching, notable signature structures. And mixed amongst those are mid-sized to smaller structures. And guess what projects won the notable awards? It wasn't the high rise. It was the ones that were done responsible, that weren't just meeting some, I think, general structural goals. But the team that was comprised of practitioners like myself from all over the world sat around the table and said, if they're not doing something responsible that we're going to celebrate later, then what are we doing here? And so to really see that tide changing, that we have to build something that can be reused. So imagine a university. The cycles of purpose in terms of how research is done, how we use facilities, if we're not building them in a responsible way, it's not going to be something that I think is, our due diligence as engineers to supply. And to really see that on an international level, that people are willing to step up and recognize these other types of projects that are doing the right thing, I think is the future.
So we're ready maybe to have a question from the audience if there's Jeremy Bricker in the back.
One of the last slides of your presentation, you showed that by replacing the concrete floor slabs with, I think it was CLRT, you contribute to carbon sequestration. And can you explain what that mechanism is?
Yeah, the timber continues to sequester carbon. And so first, as we increasingly use the timber, we're going to want to try to develop methods that prevent it from breaking down and releasing all of that carbon. I think they're looking at the timber to continue to sequester carbon.
Thank you. Interesting.
All I want to do, since I brought this with me, this is a design guide. It's available from AISC. It's hybrid steel frames with wood floors. How to take the best advantage of both worlds by using a CLT floor system on a steel frame. So this is available for free download for AISC members and for all students.
I'll just add, we're also going to be looking at materials, perhaps to go on the top of the floor that can sequester carbon. Yeah.
And as we talked about earlier, one of the things is reuse and retrofit of buildings. So if you decide, you build a structural steel frame with a CLT floor system and you decide to build a new building, well, as soon as you put that wood into landfill, which is the numbers that Jerry saw in that chart, so much of it, I forget the number, 30 or 60% is going to landfill. That number means that now that carbon's getting released. So how do you look at, we need to repurpose these buildings so that we continue to sequester the carbon over time. And so I think, again, that's the responsible deconstruction, repurposing, and application as well.
I think with all of this, if you think of the answers to the previous question and the answers to actually this question, right, it all comes down to creativity in terms of design and creativity of how we're using materials. And again, understanding what those materials mean long-term and what happens to those materials as you reuse them or try to reconfigure something. So we need to keep that in mind in the design process, also keep that in mind in terms of the education process so that the students coming out are willing to kind of take those risks and look at things creatively.
We have a related question here on the theme of sustainability. When talking about sustainability, this is from Jack Lee. When talking about sustainability, are we focusing on carbon emissions based during the construction process, or does it also include the process during raw material sourcing, fabrication, and transportation? Are those included in the holistic sustainability analysis? A couple more thoughts kind of on the big picture of this, and maybe we'll start with Patterson.
Yeah, it's really important that as we're sourcing materials, everything he asked is really important, and all products have the capability now that suppliers are developing what's called environmental product declarations. And those are like nutrition facts on your cereal. And so those EPDs are going to quantify a lot of things. Number one, the electricity or whatever the energy source is to make it. Number two, it's the emissions in the process of making it. And number three, what's everything else that goes into that? Could be your transport back and forth to actually move the material back and forth. Other products that you're buying that are alloys, like in making steel that you're adding in. Or maybe there's other things like for me to travel here today, what's the carbon footprint of us talking about a project, and is all of that layered in? And so those different emission scopes and electricity scopes are things that as a steel producer, we're looking at every day. So if we want to reduce our embodied carbon, so the carbon that's encapsulated in the steel, we have to do marginal and exceptional things and things like our energy grid. So how are we securing the energy? And the steel industry is the largest consumer of electricity in this country. So in the states we do business, if we can change the grid that we consume, we can have huge impacts on the embodied carbon and the global warming potential of that 1 ton of steel. So whether it's the emissions we do, how we sequester carbon at our facilities, or the energy that we're actually consuming, all of those things add up so that we can lower the entire embodied carbon that goes into those structures.
I would just add that another place this can come in is use of buildings where structural engineers can have some impact. I had a project a few years ago funded in part by AISC on thermal break strategies in steel building structures. So steel conducts heat really well. If you take an infrared image of the exterior of a steel building, it'll look like there's an exhaust fan at every floor while it loses heat. So we looked at approaches for putting polymer shims and plies of steel connections to break that thermal bridge, essentially provide an insulator. And thinking about ways to do that to retain structural integrity of the facade or the structural system in general, I think is something important to consider.
Thank you. I know we have another question from the audience. If you'd like, please introduce yourself and
Hello, we met over lunch, but again, my name is Joseph Ryan. I'm an undergraduate here studying civil. I just had a quick question. So you're talking about all of these advances in sequestering carbon and having more sustainable choices when building and reusing buildings. But are the financial incentives for companies to use these new technologies starting to catch up, or is this 20 years out when these start to not affect the bottom line of someone building a new building or looking to reuse a new building? Just kind of thinking of feasibility of some of these new technologies you're talking about.
Interesting you bring that up. The building I spoke of in Lansing is the Accident Fund World Headquarters in Lansing. They don't own the building. A developer bought that and reused it, adapted it, reused it as leasing it, access fund. I can guarantee you, if it wasn't economical for the developer to do that, he would not have done it. So there are great economic advantages to reusing a building.
It's also one of those things too, that again, private industry is going to drive a lot of this innovation. We're investing and looking at technologies such as like biochar. So how do we fuel our furnaces with other things besides natural gas? How do we look at, scraps from a timber mill to actually use as fuel? So there's all these things that we're looking at. And like Larry said, we're not going to, and I say we collectively as private industry, don't just do things out of the goodness of our heart, unless there's things that we are going to be able to make money at. And absolutely, I would say 10 years ago, we were probably we need to wait for the tax incentives to get there. We're not there today, or we're not there today. We're at a place now where we can start doing these things and get return on that investment, because there are people who are willing to build buildings at in a program environment that sustainability values are of the most importance. So they're even willing to say, I want to support a company that's investing in these technologies, and sometimes even possibly pay a premium for that, because they see that that's something that's going to be attractive to tenants in the future that they can lease it to as well.
I think we have another question from the audience.
Just a quick question on the locking system. So it's very interesting. It's obviously dissipating energy, affecting the structural system, seismic event. A lot of the kind of damage will occur in your non-structural components. That's going to be a large part of having to replace those sustainability issues. So can a system like that be used to kind of reduce the structural response to protect the non-structural components?
So a couple things with respect to non-structural components. First, the deflections, overall deflections from these systems are, at least as we design them, comparable to current seismic force resisting systems. So I think the issues there on how they impact the non-structural will be similar. However, you can tune these systems. You could tune them, you could try to tune them dynamically. You could try to adjust the stiffnesses. And so through that, I think we can start to change the way we think about how we protect the non-structural systems. At the end, I briefly mentioned, I'd like to develop methods that isolate the diaphragm from the seismic force resisting system through fuses. That's going to change the dynamics of the whole system. We could do that well. I think there's a world of opportunity that's totally untapped here.
Yeah, when I was in Japan as a postdoc, we did some looking into kind of non-structural systems, and based on kind of that research, it's really important to actually start to consider the influence of the system on the non-structural system and actually incorporate that into your design perspectives as well. So that can save a lot in terms of how quickly a building can get back up in use and how much material actually has to be removed as a result of damage to.
One other point, though, is structures are condemned because the structural system is too damaged. They're not condemned because of the non-structural. And so that's one reason why attention to the non-structural is perhaps lagging. But I agree completely. We need to keep pushing for this issue.
Maybe it's related to sustainability as well. So all those materials replacing your non-structural components, that's going to affect the materials.
That's right.
So we have another question from Aditya Pradhan. How can we make sustainable cities if local governments do not want to participate?
Yeah. The best thing to do is vote for local governments that do participate. You know, as I said at the end, in many ways, this is going to require a culture shift. So right now, when owners work with architects, the architects can say, oh, I think we should do this. It's going to look beautiful. And the owner says, oh, yeah, that's a good idea, even if it costs me. But when they start talking about sustainability, perhaps until recently, calculator comes out and they start talking about cost. This is going to require a culture shift in the public in terms of what they want. And with that culture shift, I think will come a shift in the leadership. These are hard things. I mean, I mentioned at the beginning that the UK and France as nations have set major goals for 2050. We have communities here who've done it, cities here who've done it. Maybe states are starting to do it. Thinking about trying to get this national. We have a ways to go. It might pop very quickly if the Services Administration really starts to get aggressive on this.
Yeah, the GSA is in a process right now of drafting green standards that I know us and other organizations have provided comment for. Because to be honest, for the last few years, there's been a few municipalities and states who put out their own green standards or buy clean acts. And they've been really policy driven and politically driven without really science or even understanding the supply chains and materials. And so we have an opportunity to do this at scale on a national level. And while the GSA may be initially just tied to projects that have a federal dollar attached to them, there will be copycats for private construction. And how we can all have a role in ensuring that the most responsible decisions are made when that happens, I think is really where this could accelerate it at a drastic pace for acceptance.
Where also engineers play a key role in policy making, right? And having a perspective that can convince people of the reason for doing these things and the benefits for them. So keep that in mind. Any students that out there that getting involved in policy and some of those aspects is just as important as your kind of engineering knowledge. And you can really do a lot with that engineering knowledge to move policy forward.
And I don't think any of us are policymakers or politicians, but just getting involved with your ASCE chapter, Structural Engineering Institute, if you're a structural engineer like me, they keep you abreast of these things that are going to impact, you know, your licensing requirements or things that are going to impact projects that you do in the future. And little things like that to mobilize the masses, I think has been great for us in the industry.
And I also have to put in one brief plug for Northeastern University. A few years ago, we started an MS in Engineering and Public Policy. Just trying to help engineers start to address these issues more directly. We have a long way to go.
So we have another question from the audience, and this one is from Keith Harris at University of Washington. How is engineering education changing to prepare future designers to address political, ethical, and aesthetic questions? And I think we've touched on this, but I really want to ask on really education. What other initiatives are there And what other thoughts are there on how we can shape our education to really think about adaptivity, sustainability, pushing the. Maybe we can start with Jason.
I think some of the things that are being done is weaving ideas like sustainability through the curriculum, right? Not just touching on it in one particular aspect, but showing where sustainability fits as you move through the different parts of the structural engineering, civil engineering, environmental engineering curriculum. Also keeping in mind other aspects that go into how a design affects things. So looking at social justice aspects, environmental justice aspects, and making sure that there's an understanding that there is an impact that's associated with everything that you do from a design perspective, and it grows outside of that. And just teaching students in terms of how to be creative, just not looking, just looking how to do outside the box design, and giving a willingness to allow for that and some freedom to be able to explore that.
Yeah, I would agree with that completely. Inculcating a culture of innovation, invention, entrepreneurship for too long was distant in civil engineering. I think increasingly is going to be important. We have also started an MS in sustainable building systems about a decade ago to try to attack this quite directly. We're going to be launching in the fall an MS in climate science and engineering, try to look at some of the broader issues. So I think this is going to start to integrate with all aspects of civil and environmental engineering education.
Open up for questions from the audience if we have any. We have a couple more questions we can go through here from our online participants. So, we talked about the comparison in sustainability in steel, concrete, and wood construction, but this is maybe a question for Tabitha specifically. So, in what ways are U.S. steel mills increasing their use of renewable energy? And we know you touched up a little bit on this, but what efforts are there actually happening in on the side?
This is great, and this kind of dovetails a little bit what I was mentioning before. So, as we think about what the Biden administration has done with committing dollars, funds, and accelerating permitting process for offshore wind, it's super attractive. And the amount of wind power on the East Coast to power the US is there, and it's strong. And we as a steel industry are going to be there to help build that. And we think about how do we actually consume renewable energy so that we can bring down those scope 2 emissions to reduce our global warming potential of that embodied carbon. And as I mentioned before, we are usually the largest electrical consumer in the state that we do business. So the natural thought is, like in our home, we add solar panels to our roof. Can we do that at a steel mill? Sure, but it's going to be minuscule compared to the base load that's needed to run a steel mill. So what are we doing today? Today, we are looking at things that are available today, such as onshore wind. There's onshore wind that, for example, our steel mill in Sedalia, Missouri, is tied to a wind farm in Colorado, and 100% of the energy to run that comes from a wind farm 300 miles away. And so we have a contract with that power company to supply the wind and that energy to feed that rebar mill in Sedalia, Missouri. That doesn't happen on all parts of the country. In some cases, we're actually investing in what's called virtual power purchase agreements. Power is not near the grid. We're buying it and allocating it to a plant that may be normally using coal power. So that's something we're doing. We also have an investment in what's called SMRs, which are small modular reactors. So that it's not necessarily something that we talk about all the times in solar and wind, but it's nuclear energy. But it's nuclear energy that's in an encapsulated pod. So we could bring that and actually run our steel mill with nuclear energy on site. And so these small modular reactors are getting permitting done. The company we've invested in is called NewScale. And so NewScale is just one of many companies that are trying to bring this so that industries like us aren't actually using the traditional baseload power that all of us use for our commercial buildings and our homes, but to have green and clean energy on site at our industrial facilities. And how do we use this with our partners? How do other industrial partners of ours, also, and we're challenging them. We're also challenging our steel competitors. Our steel company only makes steel by using scrap through the electric arc furnace, so it's over 90% recycled content. We don't even use coal to make steel, but the blast oxygen furnace of producing steel is, again, a dirty process that other steel makers around the world use as well. And so how we challenge them to bring efficiencies to the ways they make steel and the electricity that they actually consume. AISC did a study with AISI a couple of years ago that said the same steel produced in the US on average compared to the same steel produced in China, the Chinese steel, due to their electrical grid, has 3 times the amount of the embodied carbon as the steel produced in the US. So again, responsible sourcing of steel and where you get it and how it's made, these are all questions that you should ask, and not just spec the sizes, but actually require domestic supply and accountability towards your materials.
So I'll do one last question. Do you think codes like ASC or SEI should incorporate sustainability or resiliency explicitly? And maybe we can have Larry kick this one off and have maybe this be our final discussion here.
You put me in a hard spot to talk about this.
Let's just be sure I agree with your answer.
I'll let Jerry answer it, then I'll follow up.
Oh, after you, absolutely.
I think that AISC's position would be to fund research in those areas like Jerry's doing to help us to understand it better and how the industry could adapt or to accept these things rather than police it. Let's show the advantage of it by funding the research.
Yeah, certainly I agree with that. But then I would go a step further to say on resilience, yes. I think it's time we get this into the design codes. Technologies are there. The engineers understand how to do it with existing materials. I don't think it's going to cost more. These are already getting built out there. They're revenue neutral. We need to find ways to encourage this to increase significantly. And so I'm going to stick to that. Sustainability, much broader, more complicated, and I think we see a lot going on, but I will say this, I think we need to move past lead and reliance on lead as our primary driver for the built environment. So many options there. But,
well, thank you. I know it's hard to end on a difficult question. But with this, what I'd like to just say for both our participants here in person and those online, we're here to talk to you. We're happy to meet with anybody who wants to further these questions and discussion. And I know we have even more questions that we just won't be able to get to. Follow us on LinkedIn, follow us on Twitter, follow us online, send us emails. Please feel free to ask us questions. These are the people here that are making the codes, and we will be making the codes in the future. So come talk to us, follow us online. Again, I'd like to end here and thanking our speaker, Hajjar, our panelists, Larry Cruz, Jason McCormick, and Tabitha Stein. And just to thank the Department of Civil and Environmental Engineering here at the University of Michigan and the Building the Future seminar series. So thank you to our speakers.